Good evening and welcome. I'm Dr. Maren Solis, and I'm glad you've joined us. What you're about to hear is the story of our ocean, where it came from, how it shaped everything we know, and why its history matters today. So, get comfortable and let's dive in. If you look at a map of the world today, you see a particular arrangement of oceans and continents that feels permanent and fixed. The Atlantic runs north to south between the Americas and Europe and Africa. The Pacific dominates the western half of the globe. The Indian Ocean sits between Africa, Asia, and Australia. The Arctic is a frozen sea at the top, and Antarctica an ice-covered continent at the bottom. This is the world as we know it. It feels like it has always been this way. It hasn't, not even close. There was once an ocean so vast, so warm, and so biologically rich that it rivaled anything alive in the oceans today. An ocean that sat at the centre of the world, stretching from what is now Spain in the west, all the way to what is now Southeast Asia in the east. It was warm, shallow, and bathed in tropical sunlight. It teemed with life, and it is completely gone. Every drop of it absorbed or displaced by the movements of the very continents it once separated. Today, the only traces that remain are locked in the rocks of some of the world's highest mountain ranges and in the warm, enclosed waters of the Mediterranean Sea. This was the Tethys Ocean, and its story, how it formed, what lived in it, and how its disappearance reshaped the entire planet, is one of the most dramatic chapters in the history of the ocean and of the Earth itself. To understand the Tethys, we need to go back about 250 million years, to a world almost unrecognizable from our own. At that time, all of the Earth's landmass was joined together in a single enormous supercontinent, surrounded on all sides by a single global ocean called Panthalassa, a name that simply means all seas. And on its eastern side, it had a large triangular embayment, a bay-like indentation where a warm, shallow arm of that global ocean pushed deep into the interior of the supercontinent. That embayment was the earliest ancestor of the Tethys Sea. Even at this early stage, before the Tethys had fully formed as a distinct ocean, this warm equatorial sea was already remarkable. The shallow waters around the edges of the continent were warm, clear, and loaded with nutrients washed down from the surrounding land. Coral reefs grew in abundance along the coastlines. The seafloor was covered in diverse communities of marine animals. The Tethys embayment was, in a sense, the most biologically productive corner of the entire global ocean. A tropical paradise sitting at the heart of the world. And then the supercontinent began to break apart. And everything changed. The breakup of that single supercontinent is one of the most consequential series of events in the history of our planet. It happened slowly, over tens of millions of years, driven by the same tectonic forces we discussed in episode 1. Heat rising from the Earth's interior created convection currents in the mantle, and those currents dragged the tectonic plates in different directions. The single supercontinent cracked, rifted, and slowly tore itself apart. The breakup didn't happen all at once. It was a long, drawn-out process with different pieces separating at different times. The first major split, around 200 million years ago, divided the supercontinent into two large landmasses. The northern one is called Laurasia. It contained what would eventually become North America, Europe, and Asia. The southern one is called Gondwana. It contained what would become South America, Africa, Antarctica, Australia, and the Indian subcontinent. Between these two great land masses, as they pulled apart, the Tethys Ocean opened up and began to grow. Picture it this way. Imagine pushing two enormous pieces of a jigsaw puzzle apart from each other. The gap that opens between them is the Tethys. At its peak, the Tethys was not a small sea. It was a full ocean, thousands of miles wide from east to west and hundreds of miles across from north to south. It sat directly on or near the equator, which meant it received the maximum amount of solar energy throughout the year. Its waters were warm, warmer than most of today's tropical oceans, and its circulation was driven by strong equatorial currents that distributed heat and nutrients throughout. The Tethys Ocean at its peak, roughly 150 to 200 million years ago, was one of the most remarkable environments in Earth's history. Because it sat between two large land masses, it received an enormous supply of nutrients from the rivers draining into it from both Laurasia to the north and Gondwana to the south. Its shallow margins were lined with some of the most extensive reef systems ever to have existed. Its deeper waters hosted a staggering diversity of marine life. The fossils from the Tethys seafloor tell an extraordinary story. Ammonites, those beautifully coiled shells that turn up in rock shops and natural history museums all over the world, were among the dominant animals of the Tethys. They came in an astonishing variety of sizes and shapes, from tiny spirals the size of a coin to giants over 6 feet across. Some ammonite species are so distinctive and so well preserved in Tethyan rocks that geologists use them as index fossils, markers that allow them to date rock layers from the Tethyan region with remarkable precision. The variety of ammonite species in the Tethys record is frankly stunning. There were hundreds of species, each occupying its own ecological niche, each leaving behind a beautiful shell as a record of its existence. The Tethys was also home to some of the most spectacular marine reptiles of the Mesozoic era. Ichthyosaurs, dolphin-like reptiles that had returned to the sea from land ancestors, hunted fish and squid in the warm Tethyan waters. Plesiosaurs, with their long necks and paddle-like limbs, cruised the shallow margins. Mosasaurs, essentially giant marine lizards, some of them over 50 feet long, ruled the Tethys in its later stages. These were not small or timid animals. They were apex predators in an ocean filled with prey. The Tethys was, for much of the Mesozoic era, the most biodiverse and productive ocean on Earth. One of the most remarkable things about the Tethys Ocean was its reef systems. Modern coral reefs, the Great Barrier Reef, the reefs of the Caribbean and the Red Sea, are extraordinary environments. But the reefs of the Tethys Ocean, at their peak, may have surpassed even these in scale and diversity. The shallow margins of the Tethys provided ideal conditions for reef building. The water was warm, clear, and well lit by the tropical sun. Nutrients washed in from the surrounding continents. The chemistry of the seawater was right, and crucially, the Tethys had been there for a long time, long enough for complex reef ecosystems to develop, mature, and reach extraordinary levels of diversity. Some of the limestone formations that make up the mountain ranges of southern Europe and the Middle East today are the remains of Tethyan reef structures, compressed and lifted by tectonic forces over millions of years. When you look at the white limestone cliffs of the Dolomites in northern Italy, or the rocky hillsides of Oman, or the mountains of the Balkans, you are looking at the compressed and fossilized remnants of a reef that once sat on the floor of the Tethys Ocean. Think about that for a moment. The mountains of Italy were once a coral reef. The rocks that form the peaks of some of the most dramatic alpine scenery in Europe spent millions of years on the floor of a warm tropical sea, being built up grain by grain by corals, sponges, mollusks, and microorganisms. The transformation from tropical reef to mountain peak required plate tectonics on an epic scale. But the evidence is there in the rocks, full of fossils of the creatures that built those reefs, preserved in the limestone in extraordinary detail. The reef builders of the Tethys were not always the same organisms that build reefs today. Modern coral reefs are built primarily by hard corals, animals that secrete calcium carbonate skeletons and live in a symbiotic relationship with photosynthetic algae called zooxanthellae. The Tethyan reefs went through several different phases, each dominated by different groups of organisms. Early in the Tethys's history, the reefs were built largely by sponges and a group of organisms called stromatoporoids, now extinct, but once the dominant reef builders of the Paleozoic and early Mesozoic seas. Later, as the ocean evolved, the hard corals became more important, and the reef communities began to look more like what we would recognize today. One particularly fascinating group of Tethyan reef builders was the rudists, a type of clam that evolved a bizarre, almost unrecognizable form in order to build reef structures. Instead of the flat, symmetric shells we associate with clams today, rudists grew tall, cone-shaped or cylindrical shells that they stacked together in dense colonies, creating structures that functioned like reefs. They were extraordinarily successful for millions of years and became the dominant reef builders of the late Tethys. And then, 66 million years ago, the asteroid hit, and the rudists, along with roughly 75% of all species on Earth, went extinct overnight. The reef systems they had built, however, remained as rock, waiting to be lifted into mountains millions of years later. The story of the Tethyan reefs is a reminder that what we think of as normal, the way modern reefs look, the organisms that build them, the communities that inhabit them, is just one snapshot in a very long story. The ocean has reinvented its reef systems multiple times. What we have today is not the end point of that process. It is just the current chapter. For all its richness and diversity, the Tethys Ocean was living on borrowed time. The same tectonic forces that had opened it were inexorably going to close it again. The story of how the Tethys disappeared is the story of how the modern world was built, because the closure of this great ocean created some of the most dramatic geographical features on Earth. The process began around 100 million years ago when the Indian subcontinent, which had been part of the southern supercontinent Gondwana, broke away and began drifting northward. At this point, India was not attached to Asia. It was a large island, like a continental-scale version of Australia, moving north across the Tethys at a speed that was, by geological standards, remarkable, up to 20 centimeters per year, roughly twice as fast as most tectonic plates move. As India moved north, it was consuming the Tethys Ocean, the seafloor diving down beneath it in a subduction zone. At the same time, Africa was also moving northward, and the northern continents of Laurasia were rotating and shifting in ways that progressively squeezed the Tethys from multiple directions. The ocean that had once stretched from Spain to Southeast Asia began to shrink. First from the west, where Africa's northward movement began closing the western end of the Tethys. Then from the south, as India's collision course with Asia gathered pace. Slowly, the great ocean was being compressed from multiple directions, its seafloor subducted into the mantle, its waters displaced, its margins crumpling under the force of converging continents. This process was not quiet or subtle. As the plates collided, the seafloor of the Tethys, along with all the sediment and rock that had accumulated on it over hundreds of millions of years, was squeezed and folded and pushed upward. The result was some of the most dramatic mountain building in the history of the planet. The collision of Africa with Europe, driven by the closing of the Western Tethys, produced the Alps. Think about that for a moment. The Alps, one of the most dramatic and beautiful mountain ranges in the world, home to some of the highest peaks in Europe, carved by glaciers into spectacular scenery, are essentially the crumpled remains of the floor of the Tethys Ocean. The rocks at the summit of Mont Blanc contain marine fossils. The limestone peaks of the Dolomites are ancient seafloor, thrust miles into the sky. The Alps exist because an ocean closed. But the Alps are just the beginning. The collision of India with Asia, the most dramatic continental collision in the past 100 million years, produced something even more extraordinary. As India drove into the underbelly of Asia, the force of the impact was so enormous that it didn't just fold the rocks at the collision zone. It crumpled a vast region of the Asian continent, pushing rock upward on a massive scale. The result was the Tibetan Plateau, the largest and highest plateau on Earth, averaging over 14,000 feet in elevation, and above it, the Himalayas, the highest mountain range on the planet. Mount Everest, at 29,032 feet, is the highest point on Earth, and at its summit there are marine fossils, the remains of creatures that once lived on the floor of the Tethys Ocean, now sitting nearly 6 miles above sea level. Mount Everest was once part of the Tethys seafloor. Let that sink in. The collision of India with Asia, which began around 50 million years ago and is still ongoing today. India is still moving northward, and the Himalayas are still growing by a few millimeters every year, was one of the most consequential geological events in the history of our planet. Not just because it built the world's highest mountains, but because of what those mountains did to the climate, the ocean circulation, and the distribution of life across the entire globe. When the Himalayas and the Tibetan Plateau rose to their current heights, they fundamentally altered the circulation of the atmosphere. Before they existed, air flowed relatively freely across the Asian continent from west to east. After they rose, the plateau acted as a massive physical barrier that disrupted those patterns completely. The result was the creation of the Asian monsoon system, the seasonal pattern of intense rainfall that today brings life-giving water to billions of people across South Asia, Southeast Asia, and East Asia. The monsoon, as we know it, is a direct consequence of the Himalayas. Before those mountains existed, it did not exist in its current form. The monsoon, in turn, has profound effects on the ocean. Every summer, when the monsoon winds blow across the Indian Ocean, they drive the surface water away from the coast of Arabia and the Horn of Africa. As that surface water moves away, cold, nutrient-rich water from the deep rises to replace it, upwelling on a massive scale. This upwelling makes the northwestern Indian Ocean one of the most biologically productive regions in the world. The fishing industries of multiple countries depend on it. The food security of hundreds of millions of people is connected to it, and it all traces back to the closure of the Tethys and the rise of the Himalayas. The Himalayas also had a dramatic effect on global climate through a different mechanism, one that connects directly back to the carbon cycle we talked about in the last episode. When mountains rise, they expose fresh rock to the atmosphere. Rain falls on that rock and chemical weathering begins. The same process that helped cool the planet and trigger snowball Earth hundreds of millions of years ago. The Himalayas are the largest and most rapidly eroding mountain range on Earth, and the weathering of their rocks has been pulling CO2 out of the atmosphere for the past 50 million years. Many scientists believe that this sustained weathering is one of the reasons the Earth's climate gradually cooled over that period, eventually leading to the ice ages of the past few million years. The closure of the Tethys and the rise of the Himalayas may be partially responsible for the ice ages that shaped the world our ancestors evolved in. The closure of the Tethys also changed the circulation of the ocean itself in fundamental ways. When the Tethys was open, warm equatorial water could flow in a continuous band all the way around the globe, from the Pacific through the Tethys and back again. This global equatorial current distributed heat evenly around the planet, keeping temperatures more uniform from equator to pole than they are today. As the Tethys closed and that current was blocked, the distribution of heat in the ocean changed dramatically. The poles became colder relative to the equator. Temperature gradients increased. Ocean circulation patterns reorganized. The deep ocean began to circulate differently. The world's climate system was rewired. It is not an exaggeration to say that the closure of the Tethys Ocean is one of the primary reasons the world looks and feels the way it does today. The mountains of Europe and Asia, the monsoon rains, the productivity of the Indian Ocean, the gradual cooling that led to the ice ages, the distribution of species across the old world, all of it connects back, in one way or another, to the disappearance of that warm, tropical sea. When an ocean disappears, it does not vanish without a trace. The Tethys Ocean left behind a remarkable collection of remnants, some geological, some biological, some that continue to shape human life today in ways most people never stop to think about. The most obvious remnants are the mountain ranges we have already talked about. The Alps, the Himalayas, the Zagros Mountains of Iran, the Caucasus, the Carpathians, the ranges of Turkey and the Balkans. All of them, to varying degrees, are the product of the Tethys closing and its seafloor being crumpled and uplifted. The limestone and chalk that makes up so much of the scenery of southern Europe and the Middle East is Tethyan seafloor sediment. Billions of tiny shells and skeletal fragments of marine organisms that drifted to the bottom of the Tethys over millions of years, accumulated in layers thousands of feet thick, and were eventually compressed into rock and pushed skyward. But perhaps the most significant thing the Tethys left behind is something you might not immediately connect to an ancient ocean. Oil. The vast oil and gas reserves of the Middle East, the largest concentration of petroleum resources on Earth, reserves that have shaped the geopolitics of the modern world more profoundly than almost any other geographical feature, are Tethyan in origin. The oil deposits beneath Saudi Arabia, Iraq, Iran, Kuwait, and the other Gulf states are the compressed and transformed remains of organic material, the bodies of countless billions of marine organisms that accumulated on the floor of the Tethys Ocean over tens of millions of years. When marine organisms die, they sink to the seafloor. In most parts of the ocean, they are broken down by bacteria and scavengers before they can accumulate. But in certain conditions, particularly in warm, shallow, poorly oxygenated basins, like parts of the ancient Tethys, organic material can accumulate faster than it breaks down. Over millions of years, these organic, rich sediments are buried under later layers of rock. The pressure and heat of burial transforms them slowly into hydrocarbons, petroleum, natural gas, the energy that powered the Industrial Revolution, that runs most of the world's vehicles, that plastics are made from, that heats millions of homes. A significant proportion of it came from organisms that lived in the Tethys Ocean. The Tethys didn't just shape the geography of the modern world, it fueled its economy. The Mediterranean Sea is another Tethyan remnant, and its story is remarkable in its own right. The Mediterranean is what remains of the western end of the Tethys, trapped between Africa and Europe as the two continents push together. But the Mediterranean's history is far stranger than simply being a leftover sea. Around 5.96 million years ago, the connection between the Mediterranean and the Atlantic Ocean through what is now southern Spain and northern Morocco was closed off by tectonic movements. The result was extraordinary. Cut off from the Atlantic, the Mediterranean began to evaporate. Over a period of perhaps a few 100,000 years, the entire Mediterranean Sea dried up almost completely, leaving behind a vast, scorching, salt-encrusted basin more than 2 miles below sea level. This event is called the Messinian Salinity Crisis, and it is one of the most dramatic things that has happened to any body of water in the relatively recent geological past. Then, around 5.33 million years ago, the Atlantic broke through again, probably through a channel in what is now the Strait of Gibraltar, and the Mediterranean refilled. The waters of the Atlantic poured in, initially in a massive waterfall that may have been the largest in Earth's history, gradually filling the empty basin over a period of months to thousands of years, depending on which scientific model you follow. The Mediterranean, as we know it today, the sea that cradled the ancient civilizations of Greece, Rome, Egypt, and Carthage, is the result of that refilling. The Tethys Ocean was not just remarkable for its physical scale and its role in shaping the geography of the planet. It was also one of the most important evolutionary theatres in the history of life. Many of the animal groups that dominate the modern ocean trace their origins, or critical phases of their evolution, to the Tethys. Take whales, for example. The story of how whales evolved from land mammals back into the sea is one of the most extraordinary evolutionary stories ever told. It happened in the Tethys Ocean, specifically in the warm, shallow coastal waters along the northern edge of Gondwana, in what is now Pakistan and India, around 50 million years ago. The earliest ancestors of whales were land-dwelling mammals, hoofed animals, somewhat like large deer or small hippos, that began spending increasing amounts of time in the water, probably hunting fish in the shallow coastal seas of the Tethys margin. Over millions of years, their bodies changed. Their hind limbs shrank and eventually disappeared. Their front limbs became flippers. Their nostrils migrated to the top of their skulls to become blowholes. Their tails broadened into flukes. In the shallow, warm, food-rich waters of the ancient Tethys coast, the ancestors of every whale, dolphin, and porpoise alive today made the transition from land to sea. Fossil whales from the Tethyan region, including some of the most transitional forms ever found, animals that were clearly part land animal and part marine mammal, have been discovered in the deserts of Pakistan and Egypt. These fossils are found in what are now dry, barren landscapes, hundreds of miles from the nearest coast. They are there because those landscapes were once the shallow coastal margins of the Tethys Ocean. Finding a whale fossil in the Egyptian desert is not a paradox. It is a reminder that the desert was once the sea. The Tethys was also crucial in the evolution of many fish groups, sea turtles, sea snakes, and the marine invertebrates that dominate today's tropical reefs. The warm, stable, food-rich environment of the Tethys provided ideal conditions for evolutionary experimentation and diversification over tens of millions of years. As the Tethys closed and its area shrank, the species that had evolved there were pushed into the remaining warm ocean environments, the modern Indo-Pacific and Atlantic tropical regions. The extraordinary biodiversity of the Indo-Pacific reef system today, the highest marine biodiversity on Earth, concentrated in the waters of the Coral Triangle in Southeast Asia, is in large part the legacy of the Tethys. It is the biological inheritance of an ocean that no longer exists. The modern Red Sea is another direct descendant of the Tethys, formed as the Arabian Peninsula split away from Africa along a rift zone. The Red Sea is, in geological terms, a very young ocean, only about 30 million years old, and it is still growing, widening by about an inch per year as the African and Arabian plates pull apart. It is essentially the Tethys in reverse, an ocean being born rather than dying, and in its warm, clear, relatively undisturbed waters, it hosts some of the most pristine coral reef ecosystems remaining on Earth. Ecosystems whose ultimate ancestors lived in the Tethys millions of years ago. Even the animals that eventually left the Tethyan Ocean and colonized the land carry its legacy. Sea turtles still return to tropical beaches to lay their eggs, beaches that in many cases sit on rock formed from Tethyan sediment. Seabirds whose evolutionary ancestors fed in the Tethys still soar over the remnant seas that replaced it. The biogeography of the modern world, which species live where, how populations are distributed, which groups are found in both the Mediterranean and the Indian Ocean, but not in between, is a map of the Tethys's influence. How do we know all of this? The Tethys Ocean disappeared millions of years ago. There are no photographs of it, no eyewitness accounts, no direct measurements of its temperature or chemistry. Everything we know about it comes from the rocks and fossils it left behind, and from our understanding of the tectonic processes that opened and closed it. The science of reconstructing vanished oceans is a detective story of the highest order, and it draws on an extraordinary range of disciplines. The most fundamental evidence comes from paleomagnetism, the same technique we mentioned in the Snowball Earth episode. Rocks record the direction of the Earth's magnetic field when they form, which tells us the latitude at which they were deposited. By measuring the magnetic signatures of Tethyan rocks from different ages and different locations, scientists can track how the ocean floor moved over time and reconstruct the positions of the continents and ocean basins at different points in Earth's history. Fossils are equally important. The Tethys left behind an extraordinarily rich fossil record. Ammonites, rudists, marine reptiles, early whales, reef corals, foraminifera. Each of these organisms has specific environmental requirements. By studying which species are found in which rocks, scientists can reconstruct the temperature, depth, salinity, and nutrient levels of the ancient Tethys with remarkable precision. The oxygen isotope ratios preserved in fossil shells are particularly useful. They act like ancient thermometers, recording the water temperature at the time the shell was formed. In some cases, scientists can determine the temperature of the Tethys Ocean at a specific location 100 million years ago to within a degree or two. The chemical signatures in the rocks are also revealing. The thick layers of evaporate deposits, salt, gypsum, and other minerals left behind when seawater evaporates, that are found throughout the Middle East and Mediterranean region tell us about periods when parts of the Tethys were cut off from circulation and began to dry out. The organic-rich black shales that host the oil deposits of the Gulf region tell us about periods of low oxygen and high biological productivity on the Tethyan seafloor. Every layer of rock is a chapter in the story. The Tethys has also left its mark in the DNA of modern organisms. Biogeographers, scientists who study the distribution of species and use it to reconstruct past environments, can trace the evolutionary relationships between organisms living in different parts of the world today back to common ancestors that lived in the Tethys. The fact that certain fish, coral, and invertebrate species have close relatives in both the Mediterranean and the Indo-Pacific, but nowhere in between, is a direct signature of the Tethys. These populations were once connected by the ocean and became isolated as it closed. We began this episode by saying that the arrangement of oceans and continents we know today feels permanent and fixed. By now, it should be clear that it is anything but. The Tethys Ocean, warm, vast, and biologically extraordinary, existed for over 200 million years. It hosted some of the most spectacular marine ecosystems ever to have graced this planet. And it is completely gone, replaced by mountain ranges, deserts, oil fields, and enclosed seas. The story of the Tethys is a story about impermanence on a geological scale. Nothing about the physical world is fixed. Oceans open and close. Continents drift. Mountains rise from seafloors and are worn back down to plains. The world we think of as permanent is in constant, slow-motion transformation. The ocean floor beneath the Pacific right now is being subducted beneath Asia, just as the Tethyan floor was subducted 50 million years ago. In another 250 million years, the Pacific will be significantly smaller. The Atlantic may have closed. A new supercontinent may be forming. The oceans of the future will be as unrecognizable to us as the Tethys is today. The Tethys also reminds us how deeply connected the physical and biological worlds are. The closure of an ocean built mountains. Those mountains created weather systems. Those weather systems watered continents and drove ocean circulation. That circulation fed fisheries. Those fisheries fed civilizations. And the organic remains of the creatures that swam in that ancient sea powered the Industrial Revolution and the modern global economy. Every barrel of Middle Eastern oil is a Tethyan animal. Every alpine ski slope is an ancient reef. Every monsoon rain over India is a consequence of an ocean that closed. The world is built from the ocean's past. Understanding the past is not just an academic exercise. It is the foundation for understanding everything about the world we live in. how it got to be the way it is, how it is likely to change, and what role the ocean has played and will continue to play in shaping the conditions for life on Earth. The Tethys Ocean is gone, but it is everywhere. It's in the limestone of the Alps, the oil fields of the Gulf, the DNA of Wales. In the monsoon rains of Asia, the biodiversity of the Coral Triangle, and the fossils at the summit of Mount Everest. The ocean leaves its mark on everything it touches, and it touched most of the world we live in. In our next episode, we dive into one of the most spectacular chapters in the history of ocean life, the age of the great marine reptiles. While dinosaurs ruled the land, the oceans were dominated by creatures just as large, just as powerful, and in many ways, even more extraordinary. Mosasaurs, plesiosaurs, ichthyosaurs, animals so well adapted to life in the sea that they gave up any connection to the land entirely and became some of the most fearsome predators the ocean has ever known. Until then, thank you for listening.